start. So, hello everyone. It's a pleasure to introduce today Ricardo Schiavon, who is a reader in astrophysics at the Liverpool John Moores University in the United Kingdom. Ricardo obtained his PhD from the University of São Paulo and occupied postdoctoral positions at the Lick Observatories at UC Santa Cruz and the University of Virginia in the United States. Before his current position in Liverpool, Ricardo was a tenure-track astronomer at the Gemini Observatory in Hawaii. Today, he's going to be telling us about a recent discovery of a galaxy within our Milky Way that came out last week. Thank you so much, Ricardo, for accepting our invitation, which ended up being incredibly timely, given all the press attention your recent work has had. You may start when you're ready.
Thank you very much. I appreciate very much the invitation. It is a pleasure and an honor to be talking to you today at this prestigious department, one that I never had the opportunity to visit and always looked forward to. And it's ironic that this is made possible by the strange circumstances in which we find ourselves. So in any case, it's a pleasure to be here today, and I thank you for the invitation. So, so today I'm going to be talking about this this discovery, or seeming discovery that we have made of a stellar system that is apparently the remnant of an accretion event that took place in the very early stages of the life of the Milky Way galaxy. So what you see here is a press release image that we put together displaying the position of the stars belonging to the system that we identified in our sample. Obviously, this is just a distribution of the stars. It does not reflect the real distribution of the stellar system itself. You know, the distribution of the stars here is governed by the selection function of the survey. Okay, so this work is the result of the confluence of three big experiments. One is APOGEE, which I'm going to describe a little bit today, the Aperture Point Observatory Galactic Evolution Experiment, the Gaia satellite, and the Eagle cosmological numerical simulations project. So we used a lot of the results of these experiments in order to produce our results. I'll start by acknowledging the contribution by many people who made this possible, starting with Danny Horta, who is the first author of the paper and my PhD student in Liverpool. My other Liverpool students, Shobit Kisko and Andrew Mason, Ted Macrith, my former PhD student who's now in Canada, Joe Pfeffer, Liverpool postdoc, Rob Crane, my colleague in Liverpool, and then the APOGEE team, which is scattered all over the world and who has made this possible. All right, so what I'm going to be talking today to you is I'll make a very quick introduction, very brief introduction to the field of galactic archaeology and the specific topic that we are studying here, which is the Milky Way accretion history. Then I'm going to describe the discovery itself of Heretics, the progenitor of the inner galaxy structure that we discovered in the galactic bulge. And then, if I have time, which is unlikely because I have a tendency to talk a lot, as those of you who already know me I will touch upon the topic of the typicality of the Milky Way, whether the Milky Way is a typical galaxy or not. Okay, so let's start by talking about galactic archaeology. What is galactic archaeology? Galactic archaeology is this a branch of astrophysics, of galactic astrophysics, that it sets itself to answering some fundamental questions. So the first question that the galactic archaeology tries to answer is, what is the current structure of the galaxy? And by structure, and structure is quoted here because we mean structure in multi-parameter space. How do the stellar populations, the stars in the Milky Way, are distributed in a space that includes variables such as a spatial distribution itself, so the spatial structure, radial velocity, velocity in 3D space, so phase space position distribution, and a distribution in chemical space. So once that question is answered, right, and we don't have an answer to the question, we're still working on it. The next question is what is the history leading up to the structure that you observe today? So how did the Milky Way came to be to the state that we see it in today? And this can be done in different ways. The more classical approach is to reverse engineer the observations using the laws of chemical evolution and dynamics, orbital dynamics, to try to trace back, right, the history of the galaxy to its original primordial state. Nowadays, with the development of more and more sophisticated numerical simulations, people are able to approach this problem now from first principles, which is a definite progress in this field. And then finally, once these two questions are addressed, the third question is, once you understand the Milky Way, you understand the structure of the Milky Way, where the Milky Way is today and where it came from, then the next question is, what does that teach us about galaxy formation in general? In other words, how does our knowledge of the Milky Way constrain galaxy formation theory? So now, answering this question touches upon a fundamental question, which is whether the Milky Way is a typical galaxy or not. So whatever inference we make about the Milky Way will have a weight. The weight of the inferences that we have on that we obtain from studying the Milky Way is going to be large or small, depending upon whether the Milky Way is a typical galaxy or not. If the Milky Way is an outlier, our ability to use the Milky Way to constrain galaxy formation theory becomes diminished. This is one of the important aspects of that question, and is a more restricted aspect of that question because it touches upon the specific field of galaxy formation theory. But then there is a bigger question related to whether the Milky Way is a typical galaxy or not. So a bigger aspect to that question, which is the fact that that's the galaxy that we live in. So so it touches upon our position in the universe, right? So we have learned since the Copernican revolution to think that we do not occupy a position that we occupy an ordinary position in the universe, that we are average, right? So, and that is a philosophical standpoint which has to be checked against reality constantly. And what I'm going to hopefully talk a little bit about today is that we are finding evidence that the Milky Way may indeed not be a typical galaxy and may differ from the average Milky Way massed galaxy at the 2 sigma level. Okay, so one of the interesting problems to address in galactic archaeology is the accretion histories of galaxies, or the Milky Way, and of course, in more generally in galaxy formation studies. Why? Because this is a basic consequence of lambda CDM cosmology, right? If you start from the primordial density perturbations and you just let gravity do its work, you naturally predict accretion histories for galaxies. So numerical simulations show those predictions to be fairly robust. Therefore, if you want to test theory, you want to go for the central predictions, and that's one of them. So in the case of the Milky Way, the galaxy for which the accretion history is perhaps best known, the accretion of satellites to the Milky Way left its footprints in the galactic halo in manners that are very easy to spot. This here on the left, you see combined of imagery in the Sloan Digital Sky Survey, selecting stars in different ways. You can highlight the presence of various streams, such as the Orphan stream here, the Sagittarius stream, the Hercules Aquila cloud. There's lots of substructure, spatial substructure that is visible in the halo of the Milky Way, and this is due to the fact that dynamical timescales are long. Therefore, that takes time for systems to mix, and you still see the footprints of this accretion history there. And the same here on the right side in the case of Andromeda. This is a distribution of stars observed by the PANDAS survey. And you see here that the distribution of stars in the halo of Andromeda also shows a lot of substructure, again, the result of a very active accretion history in the past. Now, the questions then that we try to answer in this field are like, so how much accreted versus in situ stars are there in the halo of the Milky Way? So how much of the Milky Way halo was formed within the dark matter halo of the Milky Way, and how much of that was accreted from other galaxies? What is the nature of the accreted systems in terms of what's the mass distribution? What were the star formation histories, and so on and so forth. And then what's the nature of the in situ populations? Were an original disk that was heated up, or what? So now, one of the problems here is that very early accretion history is hard to detect. What you see here, these signatures left in the spatial distributions of stars, are characteristic of more recent accretion events that happened in the past several giga-years. But if you want to see what happened in the first few giga-years of the history of the Milky Way, then mixing in phase space has taken place more efficiently, and then you require chemodynamical information. Spatial distribution itself is not enough, so then you have to, I'm sorry about that, you have to resort to Gaia nowadays in the massive spectroscopic surveys. So, so Gaia brought about a revolution in this field, which is epitomized by the recent discovery of the Gaia-Enceladus system, or the sausage, which is a small stellar system that collided with the Milky Way about 9 giga-years ago, according to the latest estimates. And this here are two of the discovery plots. This is from the paper by Amina Helmi and collaborators. What you see here, the distribution in this kinematic diagram here. This is the quadrature sum of the radial velocity in the x and z position, and this is more like the rotational position. This is the observations, and this is the simulation of a merger system with a mass ratio 1:5, and you see that the distributions are similar. And so they basically discovered a very large population of stars that are retrograde within 2.5 kiloparsecs of the sun, and they found that these stars have low alpha abundances, and they related that to a single accretion event. By the same token, the Cambridge group had already hinted at this, the existence of this system by analyzing the distributions of the stars in velocity planes. This is here is a V5, which is the velocity in the azimuthal component of a cylindrical coordinate system. This is the radial velocity in the same coordinate system. And you see here that there's a population of stars with very high dispersion in radial velocity and low dispersion in rotational velocity, which means that they have very eccentric orbits, also around, they're very near the sun. And because of this elongated distribution here, they dubbed it the sausage. Now, in Liverpool, we co-discovered this system. We don't advertise that too loudly, but we did find the signature of Gaia-Enceladus 3 days after the data release by Gaia. But the Gaia team was quicker than we were, so that's fine. So they can take the claim for the discovery. No hard feelings. But what you see here is our own discovery plot, where this is the ratio of abundance of magnesium over iron, and this is the iron abundance of the sample, a very large sample of stars in APOGEE. And the points are color-coded by eccentricity. And it's important to spend a little bit of time on this plot just so you understand what you're seeing here. So there are basically 3 components in this diagram. So there's a large number of stars here in the high alpha component of the disk, and this is the low alpha disk. So these stars, you can see, they are predominantly a low eccentricity. There is a dusting of high eccentricity stars here in the high alpha disk, but the vast majority of them are low eccentricity. It's just that the high eccentricity data were plotted later, therefore it looks like they are mostly high eccentricity, but they are not. And then the really highly eccentric population is this halo population here. So, so these high eccentricity stars, they show a distribution here that's consistent with a single accretion event. So why is that? So stellar populations are distributed in this diagram in the following way. If you look at let's focus here on the high alpha disk, which illustrates what my point is. Initially, in the early stages of evolution, you form the chemical evolution takes place by enrichment by supernova type 2, which enrich the interstellar medium very efficiently, very rapidly, in time scales of the order of 10 to the 7 years. Now, supernova type 2 contribute a lot of magnesium alpha elements to the interstellar medium, not so much iron. Therefore, the stars that are formed initially in the history of the galaxy, or in the case of the thick disk, they tend to be enhanced in magnesium over iron. They have this very high magnesium over iron. However, eventually, in time scales of the order of 10 to the 8, 10 to the 9 years, supernova type 1a, which contribute a lot of iron and not much alpha, start contributing to the enrichment of the interstellar medium. And then this relation here, which is initially flat, goes down, and the occurrence of this event, of this supernova type 1a release, forms this knee in the distribution of these stars here. And it's an interesting point, because this knee gives you a time scale for the enrichment, for the formation of the system, which is tied to the theory of stellar evolution via supernova type 1a evolution. Now, the system that we look at here, like, has there is a knee here, which is hard to see, but there is one here, which happens at a very much lower metallicity. Okay, so which means that at the same time that the thick disk formed this knee, mind you, this is always occurs at the same time, because supernova type 1a explode more or less always at the same time. So the thick disk had this 10 to the 8 to 10 to the 9 event, giga-years event in their lives at a metallicity that was much higher than the system here, which means that it built up a much higher metallicity, which means that it had a much more efficient star formation, much higher star formation rate. Okay, so it generated high metallicity much more quickly. Okay, so that's enough for Gaia-Enceladus. Now, there are a number of other systems that were identified before and after, including the Sagittarius dwarf system, the Helmi stream, and more recently, based on Gaia, there is a Gaia-Enceladus, Sequoia, Thamnus, a bunch of structures identified by the Harvard group, and then the Kraken, which was predicted by the Leiden group, the Leiden-Liverpool group. Okay, so now, but this is all outer halo, right? These are all studies based on stars that are located beyond 5 kiloparsecs from the galactic center or more. However, the inner halo is very important. Why? Because if you just take the known density distribution of stars in the halo, and you look at the concentration, how much stellar mass there is in the halo within 3-4 kiloparsecs, it adds up to about half of the mass of the entire halo contained within 30 kiloparsecs of the Milky Way, right? Center, half of that mass is within 3 kiloparsecs. So therefore, it's very important. It's very poorly known. Now, it's important also because the earliest accretion events that took place in the history of the galaxy landed there. And that's because dynamical friction brought these systems quickly to the center of the galaxy, according to numerical simulations, the most recent numerical simulations. And finally, the very oldest stars that were formed in the Milky Way are supposed to live there as well, as predicted by various groups, various different groups of numerical simulations. So, okay. However, as you know, the inner halo is within the region that we call the bulge, right? Which is a very difficult one to study. I think there are people in this audience here who know that much better than I do. So the bulge is difficult because of the very high extinction, right? And if you want to do metal poor populations in the bulge, you are out of luck because the bulge is dominated by a metal rich population due to the overlapping thin disk, thick disk, and the bar, which outnumber the inner halo by a factor of several, between 10 and 100. So it's really like looking for a needle in a haystack. Okay, so that's where APOGEE comes in. So APOGEE, as I said, is the Apache Point Galactic Observatory Galactic Evolution Experiment. Although it has APO in its name, it is a dual hemisphere survey based on the Apache Point Observatory 2.5-meter telescopes, and in its second incarnation, including the Las Campanas 2.5-meter DuPont telescope. So it's the only galactic archaeology survey that's dual hemisphere, so it does scan the entire sky. Some of the main features of APOGEE. So APOGEE is in a nutshell here. It's based on two very state-of-the-art near-infrared high-resolution spectrographs with high multiplexing power, focusing on the H-band. The advantage here, of course, is that it has benefits from much smaller extinction, and therefore can pierce the dust and see farther than any other survey into the heart of the galaxy. High signal to noise spectra, making possible precision spectroscopy of up to actually 25 elements. This is out of date, including most nucleosynthetic pathways. And right now we have already obtained spectra for 700,000 stars. So it is a survey that has revolutionized the field. But for our purposes here, the most important aspect is that for the first time, we have obtained for 10,000 stars, of the order of 10,000 stars within 3 to 4 kiloparsecs of the galactic center, all of this detailed chemistry that wasn't there before, right? This is the most important thing. That's why. And of course, then you combine that with the precision distances in kinematics from Gaia and machine learning tools to improve on the distances, then you have a powerful tool. So the reason why we discovered this is that we really entered uncharted territory. So we started with a sample of 149,000 stars, ended up with a discovery based on a few hundred stars. So that's how difficult the problem is, and that's why we were the first ones to see that. So we also have been able, on the basis of this amazing survey, to see to make other discoveries in the past. In 2017, we reported the discovery of a population of destroyed globular clusters that inhabit the inner few kiloparsecs of the Milky Way. If you add up all the mass in destroyed globular clusters there, it outweighs the entire galactic globular cluster system, the mass of all the globular clusters that exist in the galaxy, by a factor of 7 to 8, something like that, 6 to 8. So, there has not been yet an experiment or a result that showed that to be wrong. So this is an important finding. Okay, so but what did we do to discover Heretics? So we started from a parent sample of 145,000 stars roughly, with the right temperatures, the right signal to noise, etc., best distances. And this is the distribution in that diagram that I showed before, the same thing. So this is just a 2D histogram, magnesium over iron. This is again the thick disk, the high alpha disk, the low alpha disk, and this is here the Gaia-Enceladus. If you just plot here the data points for the bulge stars, only the stars that are contained within 4 kiloparsecs of the Milky Way, that's where they are. So if you just include these stars within 4 kiloparsecs of the Milky Way center, you're left with only 6,350 stars. Then look at this data in another chemical diagram, which now combines magnesium over manganese against aluminum over iron. And it has been shown by others that accreted populations tend to live in this area of the diagram, okay? And indeed you see here that there are a bunch of stars here, both in the bulge and outside the bulge, that live here. Most importantly, pay attention to the fact that the distribution here is clumpy. So we have 3 clumps here. There's a clump here of accreted populations, a clump here in situ high alpha, and a clump here with in situ low alpha. Okay, so we know, however, that there is an overlap here. This is here the same diagram now showing only the bulge stars and showing 2 chemical evolution models. One for a Gaia-Enceladus sausage kind of system, so a low mass system, one for a high mass system. And you see that they overlap here in this area. So whatever populations you find here, they are going to be accreted populations here, but not only. There is a contamination due to an in situ population here. Okay, so keep that in mind. So now let's look at how this distribution, how this chemical separation shows up in orbital space. To do that, I'm going to look at the integrals of motion plane, which is one that preserves where you have quantities that are preserved during merger events, okay? Roughly preserved. So this is here, it's energy against angular momentum. And what you see here is the entire 145,000 stars that you saw in the first plot. It's the parent sample. So now this is not corrected for any stellar evolution effects. You see some obvious structures here. There's this stuff here. So let me just show here. So this is obviously high energy, less bound, low energy, more bound particles, stars, right? The stars that are on this side here are retrograde. Stars on this side here are prograde. Okay, so for a given amount of energy, right, you can only be bound, right, with so much angular momentum. So what you see here, this very well-defined envelope here tells you where the galactic disk stars is. So this high concentration here, I forgot to mention that the whiter you get here, the more stars you have. The white little pixel here has of the order of 2,000 to 3,000 stars. Okay, so this is then mostly the galactic disk population. There's a blob here, and there's another structure here. So let's see what happens then when you include only metal pore stars in the sample. So now I'm restricting this to only the 5,000 or roughly 5,000 stars with metallicis below -0.8. Now you see that it looks a lot clumpier and less smooth, right? So there's now the blob here that you saw before becomes far more clear, and there's other apparent structures here and here. Let's keep going. So now let's look at the in situ sample. Okay, this is low metallicity stars only in the in situ part of that diagram that you showed before. And then what you see here, that blob largely disappears. You see disk stars predominantly with a high concentration here, which is dictated by the fact that our selection function is such that it contains more stars that are near the solar position. And then what happens when you include only the accreted stars? And then that's what you see. And here you have this very large blob here, and another clump here, and a less important clump right here. So this lower energy clump here is what we call our inner galaxy structure. So looking now at the distribution of the data points in the same diagram, is the in situ population and the accreted population. You see here that the chemical distinction that we have adopted does work. You do see here that disk populations, this extension here towards lower angular momentum and higher and roughly the same energy. This is what is called the splash, which is hypothesized to be a disk population that got heated due to the collision with Gaia-Enceladus. And here you see our, so this is the Gaia-Enceladus system. So let me just point it, use the pointers here. This is the Gaia-Enceladus sausage system, and this is our IGS. So the important thing here is that there's a gap in energy here that is not present here, because the disk has a smooth distribution, like all major galaxy structures have here. And whereas there's a clump here that shows the distribution here is clumpy. Okay, and we show in our paper that this gap is statistically significant, which configures then the presence of a clump at low energy. Okay, so now the key way of distinguishing a system from its counterparts, which are co-local with it, is by examining the orbital properties of this system. Right now, a long time has passed since this accretion event took place, so we expect to see a lot of mixing. However, when you look at action in action space, you do see a very important distinction in the properties of stars in this system and stars that don't belong to it. And this here is the distribution histograms showing in this case here, the angular momentum in the z direction, the rotational angular momentum along on the disk, right? So the energy, vertical action and radial action. Vertical action basically tells you just how much energy there is in the orbits, in the vertical direction, and the same in the radial direction. And you see here that the distributions between the accreted and in situ populations differ in statistically significant ways vastly. There's just no way that they look the same, no matter how you cut the samples. Even if you restrict the samples to the most metal poor ones, you still find a difference. Of course, the more metal poor you go, the more subtle the differences become. They're still there, and they're still statistically significant. So now, let's now identify here the two systems, one well-known system now, the Gaia-Enceladus system, and our IGS Heretics system. And let's see whether, let's examine their properties in chemical space. Mind you, we measure in different ways the contamination here of this IGS sample by in situ disk stars, right? But to be at the order of a fifth to a quarter. Okay. Right, so we select stars in terms of energy and eccentricity is how we proceeded. We have of the order of 260 stars belonging to the system. Now let's examine their chemical properties. Gaia-Enceladus, as I showed before, has this distribution in magnesium over iron, which goes towards very low magnesium over iron for given metallicity, unlike the disk, right? And in the red here are our IGS stars, and you see that they differ substantially in chemistry. The IGS also differs from Gaia-Enceladus in aluminium, in carbon plus nitrogen, and in nickel we use carbon plus nitrogen because these are giant stars and they undergo mixing, and the way to account to eliminate the impact of mixing is by combining these two elements. Bottom line is, this structure has abundances that are consistent with that of a dwarf galaxy, yet it has abundances that seem to be higher than those of Gaia-Enceladus, suggesting that it has a larger mass than Gaia-Enceladus. So we looked at, if you look here, this is just a check So if you look at if you just take the high alpha disk population and you project it into low metallicity, it looks like it could this could be an extension of the low alpha population, right? So what do numerical simulations tell us about it? It tells us that for the reasons that we already showed, remember that when we showed the chemical evolution models on top of that chemical plane, we showed that there's a concordance there at same metallicity. Stars tend to have the same chemistry. Numerical simulations tell us the same. If you look at the Eagle suite of numerical simulations, I don't have time to describe that here. We took the highest resolution volume, it's a 25 megaparsec volume, selected all galaxies there that are Milky Way-like in their masses, in morphologies, and then we selected those that underwent an accretion event at about the same time, Z of 2, and we looked at the chemistry of the accreted systems versus the in situ populations. The accreted systems here show in reddish orangish, whereas the in situ populations show in black gray. So the mass of the accreted system here is shown at the top. And these are only 3 galaxies, right? We found 15 in total, and they all look the same. So this is magnesium, carbon, and nitrogen. So we sample here 2 nucleosynthetic pathways, like namely supernova type 2, supernova type 1A, sorry, 3 in AGBs, right? And you see that the in situ and accreted populations overlap. So the fact that there is a similarity here between the in situ population and the accreted population doesn't mean that the accreted population has the same origin as the in situ population. Okay, now we also looked at whether, so we found that there is orbital detachment between the IGS and its co-local more metal-rich populations. So are they also detached chemically? The way to approach this problem was the following. We looked at the distribution, the spatial distribution of these, the density distribution of these populations in chemical space. Okay, and so that's what you see here. This is in that chemical space that we use to define the accreted versus in situ samples. This is magnesium over iron, and this is aluminum over iron. And you see here that in all those planes, the distributions look very clumpy, right? And then can you model that with a Gaussian mixture approach? And that's what we did here. And when you do that, you can explain the distribution here to a high degree of accuracy without the need of connecting them chemically. Okay, so in particular, the blob that makes up the IGS in all these spaces can be explained, it can be removed from the distribution without leaving a trace and without leaving a connection between it, a chemical connection between it and its more metal-rich counterparts. Finally, so how about now that I'm sure you are entirely convinced that that this is an accreted system, let's look here at the what the data tell us about its likely star formation history. So recall the brief introduction that I have made to the thigh, knee, shin distribution in this space, right, for a star forming system. Right, so this is what happens, for instance, for the case of the Gaia-Enceladus, right, which are the blue dots here, show that it has a very important shin distribution here, lots of stars in the shin, which means that Gaia-Enceladus formed stars long enough that it developed a population that was enriched in supernova type 1A substantially. So Gaia-Enceladus evolved towards the low alpha population. What you see here is that the IGS has predominantly stars with high alpha, very few stars with low alpha, which suggests that star formation was quenched very early so that it didn't have time for supernova type 1A to make a contribution to the enrichment of the gas, which again is consistent with a very early accretion event. So what we conclude then, this is my second to last slide. As I predicted, I didn't have time to talk about the issue of why do we think the Milky Way is not typical. This is one of the, this event is one of the causes of that, but I can elaborate more on that in later discussions. So, but to conclude here, so we find evidence for this, the detection of the remnant of satellite accretion that happened at redshift beyond 2, so in the very early stages of the formation of the Milky Way. This is similar in properties to the predicted Kraken, which Diderik Croysen, Joe Pfeffer, and others have predicted to exist on the basis of analysis of ages and metallicis of globular clusters in the Milky Way. I didn't have time to show that here, but our estimate for the mass of this system, which is based solely on the comparison of its chemistry with the predictions from the Eagle numerical simulations, is of the order of the stellar masses of the order of 500 million solar masses, which is roughly twice the massage of Gaia-Enceladus sausage, which means that this was the most important accretion event in the history of the Milky Way galaxy. It makes up roughly a third of its halo stellar mass. If you take the mass of the bulge, what we call the bulge, this thing we call the bulge that we don't really know what is, right? It's this mix of inner halo, mix of thin disk, thick disk, and bar. This is only a few % of the total mass. It's nothing, right? So you can explain the chemistry of the bulge entirely without taking that into consideration. Explaining the chemodynamics of the bulge on the basis of fully in situ populations. This is a harder thing to do. And then so we examine all the possibilities. You can read the paper. I gave the phone number of the paper in the first slide. You can take a look at that. And so where do you go from here? So we need more chemistry, right? We need to probe this version of the events here by analyzing additional chemistry, especially going for neutron character elements. We need more sophisticated numerical simulations to check the reality of our analysis here. It will be good to have stellar ages, right? And of course, we need increased samples. Thank you.
Thank you very much, Ricardo, for your talk. For the people
went over time a bit, I apologize.
Okay. For the people following us on YouTube, thank you for joining us. If you have any questions, please post them in the channel and we'll try to answer them.